Cool. Hi, everyone. Thanks for coming today. I'm going to talk a little bit about chaos and pain in machine learning that we've seen when speaking to people trying to do machine learning projects, and also, excuse me, the DevOps for ML Manifesto, which is some thoughts that we've put together on requirements, really, to do ML as well as software engineering has evolved to do DevOps. So before I jump into that, I just want to sort of say full disclosure, yes, like .science is here selling a product, but what I'm not going to do in this talk is to just pitch you our product. Instead, what I'm going to do is I'm going to describe to you how you could solve the problems that we solve using open source tools. And to be completely honest, I hope that you'll walk away with the sense that, yes, it's possible, but it's kind of complicated, and I'll let you sort of make your own conclusions from that. So yeah, I hope that's sort of a reasonable position. So, I mean, we believe that AI and machine learning does actually have the ability to quite seriously reinvent the global economy in a good way. I believe that it could result in a lot less people doing tedious jobs, and there's sort of a positive future vision for how AI and machine learning can impact the world. But the other thing that we've seen is that as a discipline, it really is quite immature. So it's like it's in its infancy as a discipline, and what that means is that there's lots of different data scientists, different machine learning engineers will have their own ways of doing things. They'll have their own approaches to solving problems. And that works okay when teams are fairly small, but it becomes problematic when you try and scale your machine learning teams. So some of the problems that we've seen in speaking to machine learning teams that are trying to scale are that often time is wasted on a project. It could be the time taken to set up development environments to try and make sure that things are the same from one machine to another. A lot of inefficient collaboration. Often we've seen that data scientists will collaborate by just talking to each other or using shared spreadsheets, and that leads on to the next point, which is manual tracking. When teams are manually tracking their work, it leads to a lot of scope for error and mistakes, and so we sort of see the spreadsheet full of models and data sets and code versions as a bit of an anti-pattern, that we can do better than that. Which relates to sort of the fourth problem, which is the lack of reproducibility and provenance. And if you don't have the ability to reproduce work that someone else has done, then you run the risk of not being able to go and fix a model if it breaks. You run the risk of losing information if that team member leaves. And then the lack of provenance is problematic if you don't know where a model came from, and I'll go into more detail on that. And another problem that we've seen is that models just aren't being monitored. So people will deploy models without really a good understanding of how they're behaving in production, and then models can go haywire and people don't even notice, and that can cause real pain. So I've got a few quotes from some real people that we've spoken to, and I've anonymized them, of course, because I'm not trying to point the finger at anyone, but this sort of represents the state of the industry for a large sort of subset of the community at the moment. And so one of the things people said was, in retrospect, if we'd been able to save the versions or gone back in time to see how he got his learning rates where he is a specific data scientist, it would have avoided a lot of questions from the auditors. So this was a team that had their machine learning efforts audited, and they weren't able to explain how they got certain results, which was problematic. Another one is two of the data scientists who worked on a particular model have left, and they've gone to other companies. you want to be able to see what they did and not that it's gone when it's gone. You really don't want all the knowledge about a model to walk out the door in someone's head if they leave. Another person said that a model that they had in production failed for 3 months and they lost an immeasurable amount of money. I mean, who knows how much money they lost? It could have been quite bad. Another company said that after the last audit, they were surprised by how many problems would have been solved if they'd been keeping paper logs. This might seem somewhat familiar if people are coming from a science background, like a science or a physics background or something. The notion of taking paper logs makes sense when you're doing real physical experiments, but it should be better. It should be possible to do better than that in data science. But of course, if you ask data scientists to keep paper logs or manually track everything meticulously, then that's very tedious and perhaps it's melodramatic, but they may leave. Another person said that they keep their data science team small and in the same room so that they can track their summary statistics by talking to each other and remembering. And I needn't say, really, that human minds are not the best at remembering specific numbers, especially weeks or months later. And so we have to do better than this as a community. And the funny thing is that it feels like we've been here before. The state of machine learning today, 2019 going into 2020, feels a lot like the state of software engineering back in the 90s, before the revolution, really, that was the DevOps movement. And the DevOps movement enabled version control of everything, continuous delivery, and before DevOps, it was difficult to ship software quickly because changes had to be manually integrated. People were emailing tarballs and patches around, and then manually having to integrate things. And there wasn't a notion of continuous delivery, and let alone continuous integration. And this meant that software took months to ship. And now, in 2019, software can ship in minutes. And the same kind of paradigm shift is possible for AI. There are some things that are different about AI, however, and ML, that mean that it's not as simple as just applying the same tools that you already use for doing DevOps to AI and ML. And I'll come on to that. But this, in a few words, is our manifesto. In order to achieve the kind of benefits that software saw with DevOps for machine learning, you need at least 4 things. You need your model development process to be reproducible. That means that if you're developing a model and then 9 months later the model's running in production and I need to come and look at it, I need to figure out why something went wrong with it, perhaps, then I need to be able to retrain that model from the same source data with the same version of the code, with the same parameters, and get the same accuracy, at least to within a few percent. The second thing is that my model development environment needs to be accountable, and my models need to be accountable. And what I mean by this is accountable in the sense of human accountability. So if a human is making decisions, like if a judge is making decisions, then you expect at least to be able to ask that person, on what basis are you making your decisions? And so the equivalent for machine learning is that you need to be able to ask the model, on what basis are you making those decisions? And what that means is, on what data were you trained? And so it's a sort of basic requirement for accountability that you're able to reliably trace back from a model to the data it was trained on, and also to trace back to where that data came from sort of transitively. So the training data came from processing a larger data set, and that larger data set came from some raw data, and so on. The next point is that model development has to be collaborative. And that means that I need to be able to collaborate with someone else without treading on their toes. So I should be able to take a result that they've published and try changing stuff without interfering with any work that they're doing. And then we need to be able to integrate those changes back together. This is something that's done very well in software with GitHub and pull requests. It's currently difficult to do that with the tools in data science. And then the last one is that model development has to be continuous. And so this means it must be possible to deploy models automatically without any manual steps, and then automatically, and then also monitor those models statistically. Now, what do I mean by statistical monitoring? Well, there's this problem with model development that if you already knew, so once you've got a model in production making decisions on your behalf, like making automatic decisions, then there's this, the issue is that if you already knew the right answer for any one of those predictions that that model was going to make, then you wouldn't need the model. In other words, your production data that you're actually running the model on is unlabeled, because if you had the labels, then you'd already know the right answer. So you have to use, and therefore it's difficult to automatically monitor the models in production, because you don't know what they're meant to be doing, so it's difficult to compare what they are actually doing to something. But there are statistical techniques you can use to solve this, and basically looking at the distribution of the predictions that a model is making can give you a hint that the model is behaving weirdly. And so an example of this might be an autonomous vehicle that's driving around looking at road signs, and if suddenly the number of stop signs that the model is seeing drops to 0, then there's probably something wrong with your model, or the world changed in a way that makes the model ineffective. And in either case, you really want to know about it. So those are the requirements. So now let's look at why you can't just use the exact same tools you use for software engineering to do machine learning. And the short version of this is that machine learning is actually quite a lot more complicated than software development. And so if you look at the software development lifecycle, it basically boils down to writing code, testing the code in continuous integration, deploying the code to production, and then monitoring it. And then once the code is running in production, then the monitoring will give you information about things, maybe performance problems or whatever, that will result in you going and changing the code and then pushing new updates around the loop. So it's kind of simple. Whereas machine learning is actually a lot more complex. There's data, for one thing, and the models get trained on data. And that data itself is modified by code in order to process it. Then you have the code that goes into the models. You also have the parameters that the models are trained on. And those lead to what we call model runs and data runs. And then the model runs create models, and then those model artifacts are the things that are deployed into production and then monitored in the ways that I was just describing. And so the key kind of innovation here is changing your perspective to think about not just tracking versions of code, but tracking the runs of code using input data and generating output data, and that being the unit of thing that you operate on in your system when it comes to collaboration and tracking and provenance and so on. So that's the basic idea that I'm proposing is that we should be tracking model runs and data runs, and that will actually simplify the whole thing, and it will make DevOps for ML achievable. So I'm going to quite quickly go through the model lifecycle. So this, as far as I understand it, is the basic model lifecycle that most people doing machine learning are trying to achieve. And that is they do data engineering, so they take raw data, they do feature engineering and such to create the data set that's then used, that's then shipped into training. Then once that data set is in development, people will iterate on the different versions of the code, different versions of the parameters that they're using to train that model. And then once in production, you need to push those models out through some sort of continuous integration, continuous delivery pipeline. And then once they're running in production, you need to be monitoring them. And if there is a problem, you need to be able to go back from that model that's running in production all the way around the loop. You need sort of an audit trail almost of like the things that happened all the way around this loop to result in that model being the way it is, so that you can figure out what's wrong with it if there are problems. And so now I'm going to come to the part of the talk where I explain how you can do this yourself using open source tooling. So the first thing I want to point out is that version control is really fundamental in enabling. And if you're not version controlling all the pieces, then you can't really do development well, you can't do continuous integration well, you can't do continuous delivery, and it's difficult to know what you're monitoring. And so version control and therefore reproducibility are really essential. And so, okay, you want to do reproducible machine learning, what do you need to track? Well, there are at least these three pieces that are important. You need to track the version of the environment, and that means the exact version of the Python libraries you're using, the exact version of like even which GPU you're running it on. You need to keep track of the context in which the training code is executing. You also need to keep track of the exact version of code and notebooks. You need to keep track of the exact versions of the data sets that you're using. And it's really these sort of three legs of the stool that if you don't have one of these, then you're going to sort of fall over when you come back to trying to reproduce a certain result that you got later. And so basically, it's data, environment, and code. And there are different ways of tracking those different things. Docker is very popular in the DevOps world as a way of pinning down the environment. And so you can build a Docker image, and I know this has come up in some other talks here as well. You can create a Docker image that has an exact version of TensorFlow and Jupyter or whatever tools you're using, and then you can always come back to that image later if you need to work on the model again in the same environment that you did initially. You can also use Git, and everyone probably should be using Git for version control. There are some issues with Git when it comes to data, though, or data science, which is that when you're writing code, it can be quite natural to commit every time you sort of come to an important sort of juncture in the software development process. But with data science, it's much more of a sort of creative, experimental process. So you'll be trying different parameters, tuning the data a bit, trying other parameters, especially in the experimental phase at the beginning of model development. And so when you're going through this process, it's somewhat, it's not natural to commit to Git every single time you change something or every single time you tune a parameter. And so you end up with this sort of bifurcation of process where you're creating models that you might be shipping into production, but you're not actually recording exactly the thing that it came from. You might remember to commit later. And so anytime there's a system where a user has to remember to save something after they've done a separate step to ship it, then you open yourself up to this risk of failing the reproducibility test, basically. You also have the problem with Git that it doesn't work with large files very well, and it also doesn't work very well with Jupyter notebooks. And so there are some issues around that. And so this brings me on to the open source project that we developed called .mesh, which solves the problem of versioning data and versioning large data science or machine learning workspaces. And so you can download and use .mesh yourself, and you can integrate it into your systems to help with solving this problem. It deals with terabyte scale data sets, and you can attach metadata to your commits in such a way that you can track metrics and statistics, and it's possible to build a system that tracks provenance on top of this. And a key piece of enabling technology for .mesh is OpenZFS, which is a fabulous Linux file system that I don't have time to go into. But if you're into Linux file systems, then, well, you probably already know about it. So that's really the development piece. Those are some tools that you can use to make the development of your models more reproducible, tractable, accountable, and so on. But then there's the whole of the rest of the lifecycle: continuous integration, where you're automatically testing your software, continuous delivery, where you're actually shipping it into production, and then observability and monitoring, where you're actually keeping track of the models. I'm going to go quite quickly over these bits. But continuous integration, you absolutely have to have some kind of CI system in your production pipeline. And Alex, in a minute, is going to join us and talk about the system that they built at TrueLayer that uses Circle CI, for example. And then deploying to production, it's very, very common these days to deploy Docker containers to a Kubernetes cluster. And this is kind of outside of the comfort zone of many data scientists, especially data scientists who've come from a sort of mathematics background. Software engineering and DevOps might not come naturally, but it's well worth learning the basics of Kubernetes and the basics of Docker if you're looking to actually run the models in production, because there's a whole load of problems that have already been solved by technology like this. And then when it comes to monitoring your models, the most popular project in the monitoring space, in the cloud-native space, is called Prometheus. And I highly recommend Prometheus. It's a fantastically scalable monitoring system, and it has its own query language called PromQL. And PromQL is powerful, and it allows you to really explore all of the metrics that you're recording about your model. And the other thing you'd need to do would be to instrument your model's server with Prometheus so that you can actually keep track of which models, of which predictions the model is making. Cool, so I'm now going to do some demos. They're not actually live demos because I was worried about the Wi-Fi being dodgy. But I've got two short demos. The first one is showing how with .science you can achieve all of the things that I've just outlined as being needed. And by the way, .science is built on top of this exact stack. So it is possible to build something like .science using all of these open source pieces. So basically, what we're seeing here is a Jupyter notebook that's running within the .science platform. And what we're doing here is we're training a TensorFlow model. And this is a TensorFlow model that's being trained to predict road signs, like in my previous example. Imagine autonomous vehicles driving around with cameras constantly streaming video data. And this is the kind of model that might sit within that car to say that's a stop sign, that's a 30 limit, that's a 60 limit, and to figure out how fast to drive. And so what we can see here is we might be tuning the parameters for that model to try and get a better accuracy score. And so the ds command that you see here is the .science Python library, and that allows you to flag certain parameters as being important. So if we go ahead and run those cells, then you can see that that's training that neural network. And then those parameters will get captured in the metadata in this Jupyter plugin that we've added. And then we can see those runs inside .science. And this is kind of where I'm highlighting this notion of tracking runs. So these runs are either data runs or they're model runs. And in this case, the three runs you can see on the screen are all model runs because they're all creating ML models that can then be deployed. And so you can see that it's captured, for example, a complete snapshot of the file system in the context in which that model is running there. It's then possible to compare different runs and to say, oh, look, like when we use the best results that we've had are all when we're using the large data set with the Adam optimizer, for example. And then you can see those results on a graph that can be used collaboratively in the team. So rather than using a shared spreadsheet to keep track of which things you've tried and what results you got, you can instead do it all through a nice interface that will always capture it. And the next thing to point out is that once a model's been trained, it's possible with .science to capture this provenance graph. And so this one's a little bit hairy, but it's interesting to see that by versioning all of the data, and by capturing all of the runs, and by recording the relationship between input data and output data between multiple runs, you can then collect that information together into a graph. And this is really important because it means that you can say, well, this model, which consists of these 3 files, was created by running this version of the code against these data files. And one of these data files came from one place, and these other 3 data files came from another place. And we're capturing the versions of everything all the way through. And so if there was an incident, for example, with the self-driving car, where it had a collision and, God forbid, hurt somebody, then you can go back to exactly the training data that the model was trained on, and you can pin down exactly what training set was used. And that will allow you to reproduce the problem using the information that it captured on board, and then fix the problem and then roll out a fix reliably. And without this provenance, it's very hard to do that. The last piece is that you can then, from within .science, you can click a button to deploy the model. And so there's a button here that you can click to deploy one of these models that was trained. And very simply, you can see the sort of distribution of predictions that model is then making in real time. In this example, there's a little app that you can send different road sign images to the model in order to simulate the model driving around looking at things. And you can imagine that you could set queries on in the PromQL language in Prometheus to say, well, if the proportion of stop signs that my fleet of cars that's constantly driving around the world is seeing drops below a certain threshold, then page a human, because something's changed, and we need to know when the model has started behaving weirdly. And so the point here is that .science is automatically doing this piece of work to annotate the flow of predictions in production with the labels so that it can be presented in a human-readable way. So I also have just a very, very short demo of a piece that we just got working yesterday. So I wanted to show it because it's kind of cool, I think, which is just to point out that you can now do the deploy and the monitor step. That's now gone GA on .science. So you can, in this example, I'm using Visual Studio Code, and I can just run one command, and I'm training a similar TensorFlow network here. And so by running that one command, and then I'll just sort of skip to the end here. By running that one command and then doing the ds.model command to say these files are model files, and then doing ds.publish with this flag deploy equals true, that allows you to immediately deploy that model to production. And so what you can see here is it's automatically building a Docker image. It's automatically deploying that model to Kubernetes, and then it's automatically creating that Grafana dashboard that you saw with the monitoring piece. So I'm a little over time. I want to make sure that there's time for Alex to cover his section now. So I'd like to invite onto stage Alex Spanos, who is my esteemed guest from TrueLayer, who are one of our customers. So Alex, thank you for
Luke.
Coming on stage.
Cool. Can everyone hear me? Brilliant. So thanks again, Luke, for the invitation, and thank you all for having me. My name is Alex Spanos. I work at TrueLayer. I'm a data scientist there. And I want to talk to you today about how we deployed our first machine learning-based solution to the world using .science. So how do I change slides?
Just next right button. Cool.
But before I do that, I'll just give you a brief introduction of who TrueLayer are and the problem we are trying to solve. So at TrueLayer, we build banking APIs. We started around 3 years ago. We are 75 people at the moment, and we'll grow to 200, hopefully by the end of next year. So our vision is to power the new era of financial innovation, and our mission is to grow the open banking economy. We kind of describe ourselves as a secure conduit connecting applications to the open banking infrastructure. I guess many people aren't really familiar with open banking, so a very brief introduction of what that is. It's essentially a series of reforms stemming from an EU regulation, PSD2, that kind of mandates banks to build out infrastructure to open up their systems to applications upon explicit user consent, of course, right? So the idea behind this is to stimulate innovation, competition within the financial services sector. Okay, so as TrueLayer, under the open banking umbrella, we offer products both in the payment space and in the data aggregation space. So without further ado, I'm going to describe our core product, which is the Data API. So our Data API is essentially, and this is where kind of the .science use case falls into. So the Data API is a unified and simple API, enabling the secure retrieval of financial information to a host of, like a wide array of financial providers, and the user doesn't have to worry about all the implementation details for each individual provider. So we handle that complexity. Our Data API offers a bunch of endpoints, allowing to retrieve personal information of the client, of the user, bank account, credit card information, along with balances, and the transaction history, which is the main point of my talk. So at the moment, our Data API is live in the UK. Before the end of the year, we plan to expand to Europe as well. And as we've recently secured a good funding round, we're hoping to be global in 2020 as well. So on to the problem. So as I mentioned, we are able to retrieve, our applications are able to retrieve transaction histories of their users through TrueLayer, through our transactions endpoint. What we do on top is, apart from the raw transaction itself, we add some intelligence on top of it. Specifically, what I'll talk to you about is our feature called purchase classification. So what is this? This is for purchase-related transactions, which is transactions, direct debit transactions, credit card transactions, debit card transactions. We're able to offer an extra bit of intelligence, which is category, subcategory, and merchant name, right? So it's not as simple as it sounds, because I guess if you look to the left, you can see this is like what the provider would return. So you have a timestamp, a description, amount, etc. Now, if you read the description, it's not really, even to a human, I mean, you probably can guess it's Amazon, but it's very terse and cryptic, right? And in the end, this is what we have to work with, and in order to identify the merchant and the category and subcategory. When I say category and subcategory, in this case, we could say it's shopping general, and the merchant is Amazon, right? So we have our own taxonomy for defining category and subcategory. So our main problem is to create this purchase classification service. So the data science team at TrueLayer, spawned last year, inherited a rules-based system for doing this, regexes. So I won't go into the implementation details of our regex rules-based system. I'll spare you that. But it does work quite well. So we're able to classify around 75% of the transactions flowing through our system using only a rules-based system. Okay, that's good. But the remaining 25% is almost impossible to get using rules, because you have diminishing returns. So you might add a bunch of rules, but only achieve a very small uplift in your coverage. So not great in that aspect. Also, a rules-based system is pretty hard to maintain. Banks change their transaction descriptions quite frequently, and that ends up, breaking stuff, and then which regex actually is at fault. Then you have to read regexes. I'm using the word regex a lot, sorry. And also another problem is that, TrueLayer is expanding to new geographies. So if we expand into Germany, are we supposed to, write a whole bunch of regexes for German transaction descriptions? If I'm perfectly honest, I would rather not do that. So This is kind of a textbook situation where you evolve from a rules-based system to a machine learning system. But introducing machine learning capabilities to an organization is, it's not that simple, right? So Luke covered that quite extensively before. People think it's, you just, you build a model, it's not that. It's really integrating this model in the infrastructure, the existing infrastructure, and ensuring that the DevOps, data science, and engineering teams collaborate effectively. At TrueLayer, we had additional requirements, so we wanted to be able to track all the data science experiments we do. We wanted collaboration between data scientists, and very importantly, we wanted reproducibility. So as we operate in the financial kind of services arena, it's possible that one of our predictions may be challenged in the future. And if that happens, we need to be able to have the data and the code, the exact data and the exact code that we used to generate that prediction. And this is where .science comes in to help us. So .science was able to help us in each of those steps. So before I say exactly which steps .science helped us with, I'll show you our final solution. So at TrueLayer, we run Kubernetes on AWS. And as such, we created a serving API, a Flask API, to serve the predictions of our purchase classifier. It is totally agnostic from the model itself, except for the fact that it has to be in scikit-learn, which is, a good constraint to have. Its only dependency is an S3 bucket containing scikit-learn, persisted scikit-learn model artifacts. Okay, so far so good. How do we generate those model artifacts? .science helps us. So, in any data science workflow, there is the experimentation and prototyping phase. Data scientists love Jupyter notebooks, Jupyter Lab, so it was very cool to have .science have this kind of environment, Jupyter Lab environment, integrated within the platform. So we did some initial prototyping for building our kind of machine learning pipeline in Jupyter Lab, in the Jupyter Lab environment of .science. We were able to track all the metrics, all the experiments. That was great. So we found one that we liked. What did we do afterwards? Okay, this is perhaps the most suboptimal part of the flow. We kind of manually transcribed the machine learning pipeline that we found into a Python package that is thankfully fully tested and type annotated with Python 3. So what we did then was we git tag that new version, and our friend Circle CI runs a job, initiates a job to upload that Python package to our internal PyPy repository, and thus making our model package available to the rest of the stack. So the final step here is to actually create and save the final model artifacts that are read by the purchase classifier API, the Flask API. So how do we do that? We tag a new version of the API, and that again triggers a whole Circle CI workflow. First step in the workflow is a hyperparameter optimization phase. So what that thing does is it reads from an S3 bucket, a versioned S3 bucket, the training data. It takes the purchase classifier model that's in our private PyPy repository, and it starts running a bunch of, based on the strategy that we've defined, it runs all the various kind of model runs and with the various hyperparameters. And we track all of that in .science. And I've appended a bit of an image here from a very long kind of optimization job we ran over the weekend, where we managed to break the UI.
And we got a bug fix coming for that.
Yeah. So everything tracked in .science, hyperparameter optimization. And what the hyperparameter optimization does, it creates a JSON object that is serialized and persisted in the local environment of the API that's running. Final step, we've got the hyperparameters. Final job is to use the training data, the model, and the hyperparameters to create the model, basically, the final model, and save it off to the S3 bucket that I showed you before. And there's a final step there that checks that the accuracy is within a certain, let's say, threshold. So yeah, that's more or less how we did it. And also the final run is tracked by .science. Here is a screenshot from the best performing model during the hyperparameter optimization phase. On the left, you have all the exact code that was used to generate that. And on the right, you have the data provenance. We've not taken advantage of the full feature set, so it's a bit bare, but we'll improve that in the future. This is the whole view, the whole system together. And I'll close off the presentation by showing you our .science projects supporting our purchase classification workflow. So on the top, you see an experimentation phase. The second one is essentially the final job that's fully tracked, where we write out the artifacts to S3. And the third is the hyperparameter optimization phase. So it's all nicely grouped into those projects. That's it from me. I guess what I'd like to close off with is we have a big machine learning roadmap, machine learning enabled roadmap coming up in 2020. And we're excited to be working with .science and supporting this there. And we're also hiring. My colleague Abrar is sitting there, and he would be glad to speak to any of you. So that's it from me.
Cool. Thank you so much, Alex. Thanks. And just to very quickly say, you can try the demo I showed you yourself at .science.com/deploy as of this morning. So please kick the tires and give us feedback. And just a plea from me is that we're a small startup. We are looking for feedback. We're looking for use cases. And so if any of the things that Alex or I have said today sound interesting, then please do just pull your phone out of your pocket now and drop me an email, a one-liner saying, let's talk. And it would be really cool to have some conversations. And finally, we're also exhibiting downstairs for the last few hours, so come and see us.